Welcome to the Explainer. Let's jump straight into what I honestly think is one of the most mind-bending mysteries in modern astronomy: fast radio bursts, or FRBs. We're talking about these fleeting, invisible flashes of energy from deep space that are completely upending our understanding of the cosmos. Today, we're going to break down exactly what they are and why they have astrophysicists so absolutely captivated.
To really wrap our heads around the sheer scale we're dealing with here, just look at this number: 500 million. You see, an FRB event lasting just a fraction of a single millisecond can release as much energy as 500 million of our suns. To put that into perspective, it's literally the equivalent of taking 3 entire days of our own sun's energy output and discharging it in an absolute instant. It's just a staggering, almost incomprehensible amount of power.
But here's the ultimate paradox. An FRB is a brief, incredibly intense flash of radio waves originating from deep space, lasting only milliseconds. Yet by the time these massive bursts cross billions of light years to actually reach us here on Earth, well, they've lost a lot of their punch. They actually arrive 1,000 times weaker than a mobile phone signal broadcast from the moon, so they're incredibly elusive. Spotting one is a monumental technological achievement.
So here is how we're going to unravel this cosmic whodunit today. We'll start with the ultimate cosmic mystery, dive into repeaters on one-offs, then we'll be hunting the cosmic suspects, exploring telescopes and strange clues, and finally, mapping the invisible universe.
All right, Section 1, the ultimate cosmic mystery, the spark that ignited a new astronomical frontier.
You see, the story doesn't begin with a real-time alarm going off in an observatory. Back in 2001, a massive signal hit the Parkes radio telescope in Australia, but it just hid in archival data for years. It wasn't until 2007 that astronomer Duncan Lorimer discovered it while sifting through old pulsar survey data. It completely shocked scientists. Then, skip ahead to 2012, and the discovery of FRB 121102 changed everything. It was the very first burst observed to repeat. This was a game-changer, because it proved that whatever was creating these signals wasn't necessarily destroying itself in the process.
And I think this quote from Northwestern University's Wen-Fei Fong perfectly captures why astronomers are so hooked. She says, "This new FRB shows us that just when you think you understand an astrophysical phenomenon, the universe turns around and surprises us. It really is like that, right? Just when we think we've hit the nail on the head, the universe throws us a massive curveball." Moving on to Section 2, repeaters and one-offs, the confusing dichotomy of the evidence.
Now, what's really fascinating here is the strange behavioral divide we see among our cosmic suspects. On one side, we've got non-repeating FRBs. These are your one-off events that flash once, potentially pack a higher energy punch, and then just vanish forever. But on the other side, we have repeating FRBs. These are rare, they often have slightly longer durations and narrower spectrums, and, incredibly, some are highly predictable. FRB 180916, for instance, pulses on a totally regular 16.35-day cycle. This baffling split suggests we might actually be dealing with 2 entirely different origin mechanisms. And as this chart shows us, repeaters are incredibly rare. Less than 5% of the thousands of detected FRBs have actually been seen to repeat. Because those one-off bursts are pretty much impossible to predict, the repeaters are extremely precious to researchers. I mean, they allow astronomers to point their telescopes at a known location in the sky and just wait to catch the source right in the act.
Which brings us to Section 3, hunting the cosmic suspects, interrogating the astrophysical phenomena capable of such power.
So, what is actually causing these massive bursts? Well, the leading candidates right now are magnetars. These are incredibly dense, city-sized neutron stars with the most powerful magnetic fields in the known universe. But they aren't the only suspects on the board. Violent colliding binary systems, like merging white dwarfs or neutron stars, are also high up on the list. Then we have blitzars, which are supermassive neutron stars abruptly collapsing into black holes. Or it could even be complex interactions within the glowing remnants of supernova or black holes. But because the energy scales we're talking about are so extreme, scientists really have to keep an open mind. While collapsing and merging stars are the primary focus, the scientific community impartially explores all hypotheses. This includes some highly exotic theoretical models, like the decay of superconducting cosmic strings, or even the highly speculative idea of alien light sails. Hey, everything has to be on the table when you're dealing with an unsolved mystery of this magnitude, right?
Let's look at how we track them in Section 4, telescopes and strange clues, high-tech sleuthing, and cosmic plot twists.
To solve this cosmic puzzle, we rely on the world's most advanced radio telescopes, and each one brings a really unique forensic capability. The CHIME telescope in Canada, for example, has a wide field of view and has discovered thousands of FRBs, including the very first one ever found inside our own Milky Way galaxy. Meanwhile, the massive FAST telescope in China is incredibly sensitive, tracking persistent repeaters and detecting complex circular polarization in the signals. And then there's ASCAP in Australia, which has successfully pinpointed the exact host galaxies for many of these bursts.
But, it's not always smooth sailing. There's this rather funny twist of misdirection where astronomers at ASCAP thought they caught a massive new 30 nanosecond pulse. It was huge, but it totally lacked the typical signs of extragalactic travel. Well, after some furious analysis, they realized they hadn't found a strange new FRB at all. They had just traced a signal bouncing off a piece of dead NASA space debris orbiting a mere 4,500 kilometers away. Goes to show, even the best cosmic detectives chase false leads sometimes.
But the real twist in our story is this. The initial assumption in astronomy was that FRBs only emerge from young, active star-forming regions, mostly because that's where you find those young magnetars we talked about. But then, discovering an FRB in the M81 galaxy, right inside a dense globular cluster of ancient stars, completely shattered that assumption. And recently, FRB 2024-0209A was traced to an old, dead elliptical galaxy, a literal cosmic graveyard. This major revelation means the culprits aren't just young stars. They could be a really complex mix of both young and ancient stellar populations.
Okay, on to our final section, Section 5, Mapping the Invisible Universe, using FRBs as cosmic flashlights.
So I want you to think of an FRB acting kind of like a giant cosmic flashlight. First, at its origin, a compact object releases a massive burst of radio waves. Then comes the journey. The signal travels across billions of light years, passing right through the thin intergalactic plasma. Finally, upon arrival at Earth's telescopes, the signal has been altered. It actually arrives carrying a physical record of all the invisible matter it passed through during its incredibly long journey.
And we read that cosmic record through something called the dispersion measure. Here's how it works. As the radio burst travels through space, electrons in the cosmic plasma slow down the lower radio frequencies more than the higher ones. So the high frequencies arrive at our telescopes fractions of a second earlier. That delay, that's the dispersion measure. It acts exactly like a forensic fingerprint, proving these bursts come from far beyond the Milky Way and telling us exactly how much stuff they flew through to get here.
And because of this amazing dispersion effect, scientists are actually using FRBs as cosmic probes to map the universe's large-scale structure. They're even using them to directly address the missing baryon problem. For decades, astronomers couldn't account for all the normal matter, the baryons, that should theoretically exist in the universe. But now, by measuring how FRB signals stretch and twist on their way to Earth, scientists can literally weigh the invisible matter floating in the vast, seemingly empty voids between galaxies. They're basically tracking down the universe's missing matter.
So as we look forward to the future, with massive next-generation observatories like the Square Kilometer Array coming online, we have to ask a pretty big question. What other hidden clues about the fabric of reality are currently speeding toward us right now? We are really just scratching the surface of the fast radio burst mystery. What other extreme objects are out there waiting to be discovered in the dark? That's the beauty of time domain astronomy. Just when you think you know the universe, it flashes a brand new mystery right at you.